Good afternoon. Thank you. So we saw this ODE in your prerequisites quiz at the beginning of the course. Please go ahead and solve this for me. Can you solve this by hand? Like using variable separation, dx over x is minus t dt. And then get the next step, please. So we are finally at module 5, ordinary differential equations. Just 3 more lectures, and then one review session, and then one exam away from freedom. Talking about me. Can you solve this, please, and get me the function x of t? Okay, so you would integrate both sides. Logarithm of x equal to negative t squared over 2 plus an integration constant. But if we use the initial condition, ln of x is 1 when time is 0. So that will get me c equal to 0. So the solution to this problem is x of t is exponent of minus t squared over 2. This is what we would call an analytic solution, meaning we just obtained it by mathematical manipulation at every step, some algebra leading to this function. And the goal of this module is to learn numerical techniques or algorithms to solve ODEs that have no straightforward paths for analytic solutions. So we are going to deal with problems which cannot be easily solved uh, analytically. So that's the whole point of this method or this module. To take this equation, sorry, okay, we are going to treat this problem like a problem with a known solution and use it to compare with the numerical solutions that we'll apply. Problem with a known solution, we will use it for comparison. For comparison. And usually the methods we learn in this section or module, T typically denotes a time-like variable or a time-like variable. What are the attributes of time that are different from like space? Time cannot be negative. Usually we set time equal to 0 and the value there is called the initial condition. Time only increases or goes in positive direction, and the past can influence the present, meaning we use backward derivative or backward differencing, and future cannot influence the present, meaning we are not going to do forward or central differencing in here. So everything we learn is essentially to solve time domain problems. At least in this module. Okay. So that's the basic things we need to keep track of. Okay. So look at this equation here. Okay. Look at the original ODE, and for a moment, let's not think about the analytic solution. We'll just think about what this statement says. Can you translate this ODE into simple words? Dx over dt equals minus x over t. How do you say that in words? The rate of change of x or the slope of x scales or is equal to the product of negative x and time. Just a simple read. Okay. We can think about an approximation for dx over dt using what we learned in the previous module. Can we think of a backward differencing approximation for getting the slope from, let's say you have xi minus 1 and xi, sorry, ti minus 1 and ti, at which the values are xi minus 1 and xi. Can you think of a backward differencing approximation for dx over dt? Slope equal to, tell me, what is the slope equal to if this is y-axis and this is x-axis, or this is x and this is time? Slope should be, coming, xi minus xi minus 1 divided by ti minus ti minus 1. Just writing a very simple first order approximation for the slope. With me? Yeah, okay. Okay. So if I do that, I have dx over dt equal to minus x times t, and this I am replacing with xi minus xi minus 1 divided by ti minus ti minus 1, and this is minus xi minus ti. This is a differential equation where x and t are continuous variables. This is a difference equation. It's a difference, not the word change here, not the same. Difference equation where xi and ti are discrete values that are paired together. So take a moment, look up, please. When you write this equation, it's implicit that time is continuous, space is continuous, that you can define 0, 0.1, 0.01, 0.001, and so on. When you turn this, when you replace the derivative on the left side with a difference, you are immediately going from continuous to finite resolution. And that resolution is what? The resolution is of time, in our case Ti minus Ti minus 1, which we'll call delta T. So the whole process of numerical solutions is to take a differential equation which is continuous, replace the derivative with a discrete approximation or a difference approximation, and turn that into a difference equation. Once you have a difference equation, once you have this, can you rearrange this to write what is xi? Can you rearrange this to write? Sorry, this must be xi minus 1, ti minus 1, simply because we are trying to project from I minus 1 to I. Okay, so this would be xi minus xi minus 1 equal to this term, I'll call it delta t, times minus xi minus 1 minus ti minus 1. So xi would be xi plus delta t times minus xi minus 1 ti minus 1. So we'll have time xi or x of time at 0. This is equal to 1. This is given as initial condition. And let's say we take the step of 0.1 in time. We want to compute the analytical values and the numerical values. The analytical value would be x of t equal to e power minus t squared over 2. The numerical value would be xi is xi minus 1 plus delta t times minus xi minus 1 times ti minus 1. So what I would like you to do in your notebook is to start computing both the values using the analytic formula and the numerical approximation. And this is iteration number. We'll call this 0. We'll call this first iteration for x1, that is x0 plus delta t being 0.1 minus xi minus 1 is 1 times ti minus 1 is 0. And for this is numerical, and for analytical, x of 0.1 is simply exponent of minus 0.1 squared over 2. Can you please compute that? Or if you have Excel, I mean, I'm going to use Excel, but you can also try setting it up in Excel. Do you have these two values calculated for analytic and numerical? Numerical will be easy. Whatever x naught is, which happens to be 1, 1 minus 0, which will get you 1. And for numerical, it's 1. For analytic, it must be something very, a little less than 1. It happens to be 0.9950. First, let's make sure we all get these two numbers. Please confirm to me. Thirdly, do you want to take a seat in the front rows? You seem to be struggling to see. X of t, analytical, X of t, numerical. This should be 1.0000.9950. Yes.
Solve for the different equation before doing this?
No, this is one instance where we are using the analytic solution to learn. In general, you will only apply this method for situations where you cannot obtain an analytic solution. That's the next problem. I'll give you some examples for which a known solution is not available. Yes. So if you consider this iteration to be I, this is I equal to 1. So I minus 1 is 0. So if you consider you are computing x1, you have to write this as x1 equal to x0 plus delta t times minus x0 times t0. So x0 happens to be 1, delta t happens to be 0.1, x0 is again is 1, t0 is 0. Yes.
Where the X is coming from, because you only know about I and T, but looking for the X.
This is the initial condition. That is, the first value is always given. So when you start a dynamics problem, knowing the initial position or velocity is something you know, then you ask how it'll evolve over time. So all of these are evolution over time. Yes. That is our step length. It's not something I choose 0.1. So I could have chosen 0.01 or 0.2. It's just a choice. So I'm just using 0.1 for illustration. Putting in zero, sorry, you need to ask your question quickly. We need to move faster. So what's your question? It is a choice. When we go through the steps, you could repeat the same problem with 0.2 or 0.05. You will still be able to generate a table of values or solutions. I'll talk a little bit about how you will choose time step in general. Instead of making it entirely arbitrary, I can give you some guidance how to think about it. So what is the point of taking 0? That is, if you have time 0, you want to advance the solution through time. You want to take a finite step. So what happens in the next 100 milliseconds or the next 100 milliseconds? Why would you choose delta t to be 0? You'll be stuck at 0.
I'm not talking about the step, I was just talking about, because I didn't understand what numbers you were putting in. But
For what? For this? Think about it, I'll come back. Okay. You had a question?
Yeah.
Okay, can you try again? Okay, maybe it'll resolve itself. So what will be the next time point? If our time stepping is happening in steps of 0.1, what should come after point 0.1? 0.2, right? So this is plus 0.1 gets you 0.2. So for 0.2 seconds, you want to compute both the analytic and numeric value. For analytic value, oops. So for t equals 0.2 seconds, the analytic value is exponent of minus 0.2 squared over 2. And for ti equals 0.2 seconds, we would write xi is xi minus 1 plus delta t times minus xi minus 1 ti minus 1. Apply I equals 2. So apply I equals 2. Okay. So that will get you x2 equals x1 plus delta t times minus x1 t1. What is x1? The previous time we computed this, we got 1.0000, 1.0000 plus delta t being 0.1 times minus 1.0000 times t1. T1 is this number, 0.1 seconds. So that gets us 1.0000 minus 0.01. So that is 0.9900. What is this number?
9802.
Come again?
0.9802.
0.9802. Thank you. 0.9802. 0.9802. And then the numerical value would be 0.9900. Do this for one more iteration, please. So for t equals 0.3, that is to this number, we want to add 0.3. Sorry, to this number, we want to add 0.1 and get 0.3. Do that, please. Yes.
The A there just to compare, the A X T we compare like the error percentage, I guess.
Yes, this is like truth. The analytic is the true value, and numeric is what we are getting by replacing the derivative with a difference approximation. And we'll see that this is not the only way to do this. There are other ways, but we are starting with the simplest way. Okay, so obviously the next column could be like a percentage difference between the two values. Are you getting 9704? Can you check and tell me? For the third iteration, for the numeric solution, are you getting 0.9704? It's a good checkpoint because instead of me telling you to do each number, you have to keep trying until you are able to get this so that you will figure out the pieces. Yeah,
02 instead of 0.
come again.
Again, 9702.
9702, yeah. Not sure why. Are you using Excel?
Yes.
Okay. Sure, why? Those who are trying, are you able to get 9704? Yes, Daniel. 0.927. Anybody else getting that? Yes. Okay. So let's can you tell me how you got that? That is, can you tell the equation that you used?
So I took the time for this interval.
Yes, that is 0.1.
0.3 and plus delta t, which is 0.1 times.
So this 0.9704 would be 0.9900 plus delta t, which is 0.1 times minus 0.9900 times 0.2. Is that what you did? Is that what you did?
I got the 0.927 for 4 instead. Yeah. The
For the
number
previous
three-
row?
Number 3, I got 9605. I was looking at it wrong.
Okay. So let me say this again. That is xi is xi minus 1 plus delta t times the function at xi minus 1, not at xi. It should depend on the past. This is also past and this is current. So your equation is dx over dt equals minus dx. It could also be dx over dt equals f of x comma t. It will be any general function. That's our next example. It will be a different function. Okay. The way we discretize this, so look up please, we are seeing this one more time so that we can resolve some confusion. So the way we see this, dx over dt is a function of x comma t. So we replace this as xi minus xi minus 1 divided by delta t equal to f of xi minus 1 comma ti minus 1. So that gives us xi equals xi minus 1 plus delta t times f of xi minus 1 times ti minus 1. So let's consider this third row. Okay. We want to obtain x3. X3 should be equal to x2 plus delta t being 0.1 multiplied by minus x2 times t2. So this is t2, this is x2. So one thing you might have done is to use some analytic value in the mix. That could also cause confusion. But let's plug it in and see. X2 is 0.9900 plus 0.1 times negative 0.9900 times 0.2. Shall we do this? I don't know why I'm doing this by hand.
Really gonna get 9702.
Okay, that gets us 972 or 9702. This is 9702. So those who got values other than this number, please look at this, make sure you put in the numbers correctly. Everything on the right side must be past values. The previous time step, the previous time and the previous x value, they all together determine the current x value. Okay, so if you confirm that you are able to get this number, then we can move to the next iteration. Are we good? Those who are trying, are you able to get 9702? Yes, no, yes. Are you able to get?
I'm probably doing,
Come again?
I'm probably doing something wrong because I can figure it out.
But, I mean, forget these two steps, at least, are you also substituting the same numbers?
Mhm.
Okay, if you start here, you should end here, so you can figure. Others, are we all getting this 9702? Okay, let's proceed to the next iteration, please. So the next iteration, if we do it for I4, X4 should depend on X3 plus delta T times negative X3 times T3. Now this is time, this is T, not dt. And this is dt, not T. It's an important distinction not to mix up. So this will be, so you should use this row 0.9704 plus 0.1 times negative 0.9704 times 0.3. Nine four one three. This should come out 0.9413. Again, since the very first method we are learning, I want to make sure every step you are getting these numbers.
The error percentage keeps increasing, like, there's a reason for that.
Yes, there's a reason for that. I was going to talk about it, but the simple or the short version is you are replacing the derivative by looking one neighbor back, and you are having a finite width of the discretization time. The error in this scales as order of delta t. As you make delta t smaller, the error can be improved. And then there are other ways to improve that. Those are the methods we are going to learn. So this is by far the most inefficient method you will learn, but we'll learn a more efficient method from.
It's similar to like bisections, how
It's kind of it's a learning tool. Then we'll learn something better. So since Rashid brought up the percentage difference, can you also compute what is the percentage difference using the analytic as the reference? You want to define this as 1 minus x numerical divided by x analytical expressed as a percentage. So is everybody getting 9413? Yes, no? Those who are even trying by hand, you should be able to get this. 9413. Okay. So percentage difference, I have those computed. One second. Yes. Did you have a question? No. So please compute the percentages for these three entries. And you can see for yourself what he mentioned, that the percentage difference keeps increasing. Please do that. Okay, am I the only one hearing this? Okay. Just making sure before I go raise some complaint.